Hey folks, what are we doing? We're doing chapter 5. We're getting into sensation and perception. So let's have a quick vocab lesson as we dive into this. So a couple of terms for you. Sensation and perception are different things. In the vernacular, in just like we're speaking English to each other on the street corner, maybe they're not different. Psychology, science in general, psychology in particular, has a bad habit of like picking up words that are already in common use and then putting our little scientific spin on them, and then expecting everyone to understand. Let's do our terms. So sensation, we're talking about stimuli, energetic impulses zipping around through the universe or bodies bumping into things. And there's nerve endings, they're essentially identical to the neurons in your brain, but there's nerve endings that terminate in the environment somehow. They bump up against one of these energetic stimuli, collect them, and that's data. And then we convert into a neural impulse, right? So a nerve ending in your hand touches a thing, it stimulates that nerve ending kicks off a neural impulse, goes through the nerves in your arm up into your brain, and then it's playing around with the neurons in your brain, the neurons that terminate at other neurons, right? And that process of conversion from an energetic stimulus in the universe to a neural impulse, that's called transduction. Okay, good enough? Wonderful. So, perception is when the appropriate part of the brain for that sense gets a hold of all that data and processes that data such that the data becomes. So in the eye, you have the retina, and it's just light receptors gathering light and going ooh ping, right, and telling the brain every time it's getting a ping. And then in the occipital lobe, that part of the brain is kind of keeping track of all the times cells in the eye were stimulated by light and organizing those into meaningful information. And then sending that information forward to your brain, and then, right, so data into information, that's the perception part. And then it gets shipped forward to the frontal lobe where it can be made conscious. And when we're conscious of it, we have knowledge, okay? So data is a set of facts, points that are meaningless until they're sorted through some frame. For example, numbers in a grid. If you don't know what the numbers mean, if you don't have the frame that organizes all these ones and zeros into bars of 8 bits and buses and sorts out that this is satellite data and this is the temperature of the battery and this is the input from the solar panels, how many watts per second are being generated and so on. It's just ones and zeros. Without that frame, useless. Right? There's no inherent meaning in data. I'm going to show you a Bo Lotto video when we get to perception, and Bo is going to misuse these words a little bit. No problem. What he's trying to say is going to be pretty clear. And information, once that data is sorted through a frame such that it has become meaningful, right? And then knowledge, once you're aware of that information, you have consciousness. All right. So this lecture is going to be about sensation, not so much about perception. That's the next lecture. So how many senses do you have anyway? What do you think? Come on now. If the answer were 5, would I be asking? Exactly. Think about it for 5 seconds. You know you have more than 5 senses, right? Don't say 6. Come on. This is a science class. Um, how many senses do you have? Well, it depends how you define a sense. You can get in all kinds of trouble starting this discussion without operationalizing your terms first. So for our purposes, a sense means that it has a discrete collection apparatus and it has a part in the brain where it's processed individually. Um, so scientists who study this stuff are going to come up with between 9 and 21 senses. And it's really in that equivocation, really in that definition. So what do we have? I mean, the 5 basic senses: vision, audition or hearing, olfaction or smell, gustation or taste, touch, Asian? How many senses is touch? We're used to talking about it as one thing. Is it in fact one thing? Well, you sense pressure through your skin. When you're feeling textures, this is soft, this is hard, this is rough, this is smooth. It's just variations in pressure against the skin. So that's one. And your skin contains pressure sensors. They can be really fine. You can train yourself to sense the barometric pressure, right? Without that little mercury bar, you can just tell the storm's coming. I can feel it in my bones. Temperature. So your skin has discrete sensors for cold and warm. And when they get overwhelmed a little bit, cold and warm activate at the same time, and that gives you hot. So there's actually an illusion, a non-optical illusion, where you can take 2 pipes that are twisted together, run cold water through one, warm water through the other. A person gripping it will pull away as though it were scaldingly hot. Are those individual senses? Well, we have individual receptors for cold and for warm, but they seem to be processed in the same part of the brain. So we might say temperature, yes, cold and warm, no. So depending how you answer that question, right, you're already up to sight, smell, hearing, flavor, and then pressure, temperature, right? We're already at 6. If you want to break temperature down into cold and warm, you'd be at 7. I think we're probably at 6. What else is in your skin? Nociceptors, pain. Excesses of pressure or temperature activate the nociceptors in your skin. There is a discrete region that goes, ow, stop it, right? Pain is a sense all its own. And as an aside, emotional pain is pain. The same region of the brain that activates when we like stab you with a letter opener also activates when you feel depressed or rejected. And depression is treatable just a little bit, with aspirin. So where does that put us? That puts us at least at 7, right? That's at least 7 senses. We're not even working that hard yet. What about proprioception? The kinesthetic sense, your body's sense of its own position in space. Arguably a sense. I don't know what is the sense receptor. It's really the nerve endings in the body, but they're not nerve endings in the skin. They're specialized nerve endings that know what's happening inside. So you wake up in bed one morning and you're a weird sleeper, right? So you have one arm tucked behind your head and the other arm's thrown out there and your legs are in different places. And you don't have to look up at the mirror on the ceiling to know how your body's organized. You just know where all your parts are, okay? We're on the ceiling, just me, pink champagne on ice. The Eagles, man. Yeah, so there's that proprioception, and all that stuff is down there. It's in cerebellum, right? Cerebellum knows your body position in space. So arguably arguably a sense that would give us, what, 8? Still not trying very hard. What about balance? You have a couple of ways of knowing balance. One is looking for vertical and horizontal lines in the environment, and your brain sort of orients you. So we can do illusions, right? We can give you visual stimuli that you're moving or tilting to the side and get you to inappropriately correct. You get that sense of movement and stuff. The other, though, doesn't depend on vision, and so is its own sense. In the cochlea, you have receptors for pressure, right? Hearing is little hair cells. We'll talk about those later. But in the cochlea, there's fluid in this like weird loopy shape thing, and your brain knows which way gravity's pulling on that fluid. Okay, so if you sit in the spinning chair and you spin around, you can do this experiment actually at the Natural History Museum in Denver. You sit in the spinning chair and your hearing and your vision get blocked off, and you're supposed to signal with your thumbs which way you think the chair is turning, and then they spin you this way, and you go, right, the chair is spinning this way, but they keep it up for like 15 seconds, but then you slow to a stop, and you keep pointing as though you're spinning, because that fluid in your ears is spinning, and because of momentum, it takes like fully 2 minutes. Right? That's why you feel dizzy after you spin, and you feel like you're still spinning and you overcorrect. And that is for keeping you upright. Your brain knows your head's orientation in space because of those little cochlea things that are full of fluid. And that's processed again in a region down in the cerebellum. So we have a distinct brain spot, we have a distinct collection apparatus. That's a sense we're at 9. Now we're still not getting controversial, like magnetic sense. We know that sharks have iron filaments in their snoots, and those filaments kind of change direction based on the magnetic field that they're swimming through, so they can sort of chart the world in magnetic fields. Can we do that? Yeah, not really. No evidence that that would be true. It's a sense that another animal could have that we don't. Electricity, you can sense strong electric fields, but is that its own distinct thing, or is it just your hairs standing on end and you're getting that information through your skin? Probably the latter. So to get to that 21 number, you have to like break everything down into tiny little pieces. I think. Like the eyes, you can get red, green, or blue. Yeah. And is that 3 individual senses or just one? We're going to call it 1. All right. So how many senses do you, it's just another case of like you learn stuff and everyone says it's one way, but when you look at it closely, it's the dumbest thing you ever heard, right? Obviously, you don't have 5 senses. We've taken to saying the 5 major senses to keep people happy about the 5 senses thing. I want to move you forward though. All right. Waveforms. To talk about senses, we have to understand waveforms, at least at this most basic level. You can even ignore the equilibrium point. All right. Waveforms, for our purposes, have 2 characteristics. They have amplitude or magnitude or intensity, and that is the distance from the 0 line to the top, or to the bottom. That would be negative amplitude. And the wavelength is from peak to peak, and the frequency is from peak to trough. That's the number that we're interested in: frequency, peak to trough. Okay, top of the peak, bottom of the trough, frequency. How often do peaks arrive? All right, and we measure that in hertz and megahertz and all that stuff. Okay, just how many thousands per second. All right, so that's the basic structure of waves. What does that mean to us? Well, it depends. Are we talking about light or sound? If we're talking sound, then the amplitude or intensity is the brightness. What do we mean brightness? We mean there's a bunch of receptors for light in the back of your eye, in the retina. And when light passes through the eye, it has a percent chance to activate any of the receptors that it gets close to. Now, the taller the wave, the more of a chance it's going to run into one of those receptors and knock it so that it produces a neural impulse. Get to that in a second. All right. So, really high amplitude light, it's not just one photon coming in at high amplitude, right? The higher the amplitude, the brighter the color you seem to see. So we're talking fluorescent colors and anything pastel shaded out to white. It's activating a bunch of receptors. The wavelength gives you the hue. So the electromagnetic spectrum is vast. There's a tiny little portion of it comparatively, which is visible light, which goes ultraviolet at the high frequency end to infrared at the low frequency end. And humans see kind of between those, not including, but between those points. Other kinds of animals see other kinds of light. Snakes hunt with heat. That's going to be in the infrared range of light. They don't see the light, they feel the heat, but animals that see well in the dark might be a little more in that infrared range. Flowers, you ever look at a flower and go, well, that's pretty. Yeah, but it's not for you. Flowers are landing pads for bees. Bees see in the ultraviolet. So if you can convert the ultraviolet into false color that's available to humans, flowers look completely different. And bees love them. It's like landing pads, land here, there's snacks, right? Like that. Good. So you put all this together and you get this kind of a thing. This is a color picker from like any computer program that deals with color. And here you are going to pick your hue. So red into yellow, into green, into blue, into red, right? So here's your hue, and then here's your intensity. So as you get more and more receptor sites activated in the eye, higher and higher intensity light, the red here is going to wash out towards towards white. So you're going to move from red into sort of the pinks and the pastels into nothing. And then as the intensity decreases, well, that means you're not activating any receptor sites, right? And no receptor sites activated means you see just black. Okay? Good. When we're dealing with sound, we're saying the amplitude, that tallness of the waveform, that's volume. The stronger the pressure wave, the higher pressure air being pushed along. Again, the more chances you're going to activate the cilia in the cochlea. You're going to get really intense, high volume sounds. The frequency is going to be the pitch. The more times per second that the cilia get activated, the more times per second we hit the peak, the higher pitch sound you hear, right? From Minnie Mouse down to, I know who's a character with a deep, deep voice. I know me, I guess. Okay, good. Fine. So now we have to talk reification, don't we? There are no waveforms. There's no such thing as a wave. The waves in the ocean, sure, But that's not what we're talking about, is it? Right? A wave is a wave. A waveform, a mathematical waveform. Why? Same problem as triangles. It's a 2D function. It's a function. It's not even a geometric figure now. It's just a function. And that's not a 3D shape, but we're dealing with 3D phenomena, right? Things that exist in the universe have 3 dimensions, not 2. What I want you to know here is that the map is not the territory. What do we say? Well, with light, it's complicated. With light, the waveform is really a probability function. You can't definitively say where a photon is at any given moment in time. And when you try to measure it, you get really weird results. But basically, the waveform is saying there's X probability that the photon is in this zone at this period of time as it crosses through space versus this period. You can still find it down here. It's weird. The waveform is a probability function. Everything in the universe moves in a straight line. It doesn't funky chicken through the universe like this, okay? That's nonsense. Photons aren't zipping through the universe up and down. They're going in straight lines. But it's a probabilistic function where in a zone they are at any given moment. Oh, you've seen things curving. All right. Space, like light going around really super dense phenomena. Okay. It is moving in a straight line, even though it seems to be curving. All right. Satellites going around the Earth are moving in a straight line, not a circle. The circle is subjective from our point of view. What's happening is that gravity piles up space so that there's less, Earth is down here, object going this way, right? And the object is encountering more space here than here, okay? So if it goes 1 meter, but 1 meter doesn't mean the same thing on each side, right? It's going through maybe 1.01 meters here because there's more space. Versus 1.06 meters here because there's less space. There are less meters in a meter on this side. But what happens when you're driving a tank, right? The 2 treads, and you run 1 tread slower than the other tread, you're going to go this way, right? Yes? Well, that's light. Light is moving through the universe in a straight line. It's just that space isn't what you think it is. That's really complicated stuff. And it's much easier to explain the reification thing with sound, all right? So what are we looking at? We're looking at something like this probably. Take off the labels, and this could be a reading on an oscilloscope. An oscilloscope just measures pressure over time. Hang on a second. Excuse me, allergies. Pressure over time. What does that mean? That means we have a collection device. It's usually just a tube. It looks like a big marker when you pull all the marker stuff out of it. And at the bottom, there's like a flange, and it's measuring how much pressure is on the flange, right? And that pressure changes over time. And as time goes by, you collect a measurement every 1/10 of a second or something, and then you plot those on an XY axis, right? Y is time, X is pressure. As time goes by, the pressure changes, right? And it tends to make this form because why? Well, because there's a finite amount of air in the atmosphere. And in order to make a high pressure zone, right, that's what speech is doing. I'm making a high pressure zone, increasing the pressure. Well, that means I have to collect that air from somewhere. And then the air around it's going to collapse afterwards and then rebound in terms of pressure, right? It's like going to the beach and you dip your your shovel in the sand, and then you put a pile of sand next to it, right? So you get a peak and a trough, right? So when I'm speaking, that's what I'm doing, is I'm gathering up air and I'm forcing it out through the larynx in a concentrated fashion, and that air density is gathering here and then sort of dissipating through the environment. That's why sound loses intensity over distance, especially through air, even more especially through fluid. Great. That's not a wave, is it? It is when you plot it. I'm plotting pressure over time. It goes like this, but that's just the map. But the map's not the territory. In practice, you can't see it because air is invisible. If you could color code density, you'd see like maybe a big blue patch moving in this direction, but all faster this way, but in all directions and expanding outward. And as it expands outward, it loses its blue saturation, gradually dissipates until it's gone further away, right? Yeah, that's not a wave. The way you're taught to think about this is like you can't drop a pond, drop a pebble in a pond, and then you see that ripple going out. It's only going out in 2 dimensions, right? That's just the interface between the water and the air, and it's flat. It's not going out in all directions at once. That's impossible. That's why you can't visualize it. There are no waves, okay? The wave in the pond is not the wave in the wave form. Different things. Formal definition, artificial, natural versus formal or artificial definition. Okay? So no waveforms, that's reification. Why do I keep hammering you with this? Because psychologists reify so much stuff that actually is very consequential. Let's talk about eyes. What do we have? Here's a picture of an eye I stole from the internet, Shutterstock or something. Yeah, Shutterstock. And you don't need to know all this stuff, but let's talk about the important points. Right in the front here, you have the cornea. The cornea is just a thin, transparent coating that protects the workings. You want to keep the hole and stuff covered up, right? The pupil is really just a hole. Don't want ways in and out of the body. Got to keep the ocular fluid in and clean. All right. Corneas, barely biological, barely living matter, easily transplanted. Sometimes they get occluded, they get scratchy, and you get a cataract. And then the pupil, that's just the hole where light gets in, right? The little black dot in the middle of your eye. It's a hole. The iris is if you look at an eye and you see the little black dot and then you have that colored ring around it. The color is really almost irrelevant to vision. The darker it is, on average, the brighter the light where your ancestors have been in the last 12 to 18,000 years, basically. The darkness of the iris keeps too much light from getting in so that you don't burn the retina. You can get a sunburn on your retina. It's nasty. It's called glare blind. The colder weather that your ancestors experienced, the cloudier it's been and the further you are from the sun and so on. The more it's advantageous to have a light color there, because you need vitamin D to live. Vitamin D gets in your body through sunlight. You're just not worried about sunburning the back of your eye. You can save a fractional amount of energy not making that melanin, okay? And that's it. That's the sum total of the significance of that, blue eyes and brown eyes. And then we have the lens, and the lens is this sort of ovoid shape, and it can distort. If we were looking at it head on instead from the side, then the lens is surrounded by a ring of muscle like this. And that ring of muscles can only contract and relax, right? So it can contract like this, and as it squeezes around this dimension, well, that material has to go somewhere. So if we take it side on again, as the muscle squeezes down in this direction, well, the lens has to bow outwards like this, right? To compensate. So that you're making more lens for light to pass through. That's how that thing works. Okay. Forget about this guy. Forget about this guy and that. The retina, this kind of pink thing here, that is where all of the photoreceptors live. There's a bipolar cell and a ganglion cell. The ganglion cell. Light comes through all this stuff, through this aperture, through the lens, gets redirected to the fovea, which is kind of this zone where you're trying to get light to arrive, because that's where the highest density of photoreceptors. And then it passes through the retina and hits the bipolar cell or the ganglion. If it hits the ganglion, it activates, and that sends a signal through the bipolar cell, and all those signals get bundled in the optic nerve and sent out. So we need to know here. It's probably about as far as we need to go. Yeah. Good. Lensing. So here's a picture. Oh, super crude. I know, but it's not an optics class. Right? Take a physics class. Here's a lens. Remember that thing about light always moves in a straight line through a vacuum, okay? You can curve light. You can't curve one photon, but you can curve a bunch of photons. You can change the probability that they'll arrive in a direction by making them bounce off various particles. Transparent material allows light to pass through largely unmolested, but somewhat molested. Okay, the more material that you're passing through, the slower you have to go. Right, light slows down through these materials. Now, if you're going straight ahead, then there's no deflection in your trajectory. But if you're, and you have to think of light here as having width, because the more stuff you go through, the more you get bent this way. Okay, like tank trucks, but it's individual photons. It's more like a column of files. You have 4 people marching abreast, and this one goes really fast and this one goes really slow, right? They're going to turn like this. Okay. Yeah, it's good enough on that. So the point of this being that the further away something is, the shallower is the angle at which the light's coming in. And so you don't need that much deflection to get that light out the other end to arrive at the focal point in the retina. The closer something is, though, the more likely it is to be taking up all of the retina. And so you need to clamp down, fatten this boy out to cause this deflection, so that the light bends into the fovea. What do we mean by this? I mean, like, do you have a pen? Pen will work. Grab a pen and hold it out at arm's length like that. And then with your fingers, kind of make a point your middle finger, your I hate you finger, point that at the top of the pen, and then your pointing finger, point it at the bottom of the pen, right? Okay, and that's basically the angle of attack from the pen to your eye at arm's length. Okay, cool. Now bring that pen really, really close, and you can't even do that with your fingers, right? You're going to have to use your finger and your thumb, right? And that is a much steeper angle, right? That's what I mean the closer a thing is, the more it's occupying the top to the bottom of the lens, and therefore, as it comes up to the other side, the more it's going to fill up the back of the eye, which means there's going to be a bunch of spillover into parts of the retina where you don't have that many receptor sites. You need to get it into the part where you can focus. That takes more lens, squeeze, fat. What does that give us? That gives us age-related presbyopia. So I'm kind of at that age where if you hand me a piece of paper to read, I'll play this game for a minute. Okay. And these days I lose the game. Like even 2 years ago, I'd win. I get to a point where the print was big enough for me to see and far enough away I could still focus on it, right? Now I lose, and I keep reading glasses in my desk drawer. Certainly leave these laying around the house wherever I go, in case I need to look at something close up. What's happening? What's happening is, remember, you have that ring of muscle all around the outside edge of the lens. And the muscles are held together with connective tissue, entropies everywhere. That connective tissue breaks down like the sweatpants you wear to Thanksgiving every year, and they fit both before and after Thanksgiving dinner. But after 15 years, they only fit after Thanksgiving dinner, right? The elastic is starting to break down. They're getting loose. Well, that muscle ring can no longer clamp down the way that it could because they're not the muscles aren't connected as well. It can only clamp down a little bit. Plus, you ever find a rubber band in a desk drawer and it's been there an indeterminate number of years? Yeah, how's that rubber band? Exactly, the elastins are trash, right? Well, the lens is spongy. It's made of elastic-like material. And if you make a rubber ball out of rubber bands, it's really, really bouncy. Unless those rubber bands have been in the desk drawer for 12 years, right? Entropy's everywhere. And the lens in your eye, the elastins break down, and it fills up with impurities. And so it's harder to squeeze down into those shapes. So between 45 and 50, God, I'm right there. Between 45 and 50, your eye just can't make the shape it did when you were younger. Okay. What else do we have to talk about? Probably trichromatic theory. Forgot to put that in there. Trichromatic theory. So you have 3 kinds of color receptor: red, green, and blue. I know you took an art class in 4th grade or something, and you learned that the 3 primary colors are red, yellow, and blue, but that's paint. That's reflective surfaces, not light. When we're dealing with light, all the colors are made of red, green, and blue. You have red, green, and blue receptors in the back of your eye. That means they're stimulated by light in a given range of the visible spectrum. And light outside that spectrum doesn't generally stimulate. Now, really high intensity light can stimulate colors that really aren't in their frequency range, right? Which is why the brighter the light, the more it washes out into white. If you mix paint, you get black. If you mix all the colors of paint together, it turns black, which means it's not reflecting any light. But when you mix all the light together, you get white because it's stimulating all of those receptor sites at one time. And the brighter the light, the more likely that is to happen, to just wash it all out. Okay? That's why lighter color of red is pink, and then pastel pink, and then just white. Is this making sense to people? I hope so. You have rods and cones, meaning that the cone-shaped cells are red, green, and blue, but there are also rods which are monochromatic. They fire in response to any light. They're quite sensitive, It takes less light to stimulate them because that light does not have to be in a particular waveband, frequency band. Any light will do. What that means is, being diurnal animals walking around in daytime, the rods are almost always totally overwhelmed. And so they are constantly in a refractory period and a reset period. So they're not doing any work for you right now. But when it gets really dark, power goes out, you're in the basement, dead dark. Not quite. There's a tiny bit of light streaming in from under a door 2 rooms away. If you give it a minute, okay, if you go straight from bright to total dark or near total dark, you might as well have been struck blind. But those rod-shaped cells slowly exit their refractory period. They slowly sort of, let's say, awaken and start to feed information through the optic nerve into the occipital lobe. Okay? And that's just when you're adjusting to the dark, right? You have a little adjustment period. So that's what's going on there, and I think we can be done with this. So let's talk about ears. Another stolen picture. This one's from Vector Stock. Hooray. Just so we can get a look at this guy. And what do we have here? You don't need hardly any of this stuff. If you love it, I mean, take an anatomy class. I should not be teaching you anatomy, and I'm probably going to screw this up. All right. So you have the auricle. This guy, the outside part of the ear, it's not just to keep your glasses. Okay? This is like a step down. It takes big waveforms and steps them down kind of so that they'll fit into the ear canal. Can you dig that? And the ear canal isn't really concerned about how tall the waveform is in the first place. It's barely important. You can funnel sound, and it's really concerned about pressure over time. So pressure waves, they get compressed, they arrive in the ear, they hit the tympanic membrane, which people would just call the eardrum. Right? It's a little membrane. That's why it's called a membrane. And it's like a drum head. Sound hits it. In this picture, sound hits it from this side, right? And it bows like this, right? You know what drum heads do. And then it's connected to this whole weird apparatus with the hammer and the anvil, and the whole communist flag is in there. There's a sickle, and I don't know, a stirrup or a stapes, right? And then there's another membrane here leading into this fluid-filled thing, the cochlea. All right. So this is another step down. It's taking kind of a big thing that's vibrating, and it's stepping it down to a smaller thing that's vibrating. Okay. So that pressure wave will fit into this smaller thing. This thing's full of fluid, and the cochlea is lined with little hair-shaped cells like tiny eyelashes, and those are called the cilia. C-I-L-I-A, cilia. And each of the cilia rests atop a ganglion cell. You've heard that before. This is where transduction happens, right? In light hits the ganglion cell and it kicks off a neural impulse. That's transduction. We've gone from an energetic impulse in the environment to a neural impulse that the brain can operate on. Same thing here. That fluid in the cochlea, it's moving back and forth. It's washing back and forth as it's hit, pressure going up and down, if you like, as this stirrup pounds that membrane there. So at the beginning end, you'll have your low frequency cilia, and at the tippy end, you'll have your high frequency cilia, which means these guys move like this up here, and these guys move like this down here, right? Good. And then your brain keeps track of which cilia vibrate. Every time it vibrates, it kicks off a neural impulse, and your brain knows which one where. And that's where you're getting all your sound information. Okay, happy? All right. This is a weird arrangement, isn't it? Yeah, this is a very strange arrangement right here. Why? Because your ear is doing two things. Okay, your ear is doing sound and it's doing balance, and those are two totally conflicting evolutionary demands. It's weird to have one piece of anatomy doing two fundamentally quite different jobs. What that gives us is push and pull, right? Serving two masters, which means you get a good enough system. Would there be a better way of getting auditory information? Almost. Would there be a better way of getting balance information? Yes, easily. All right. But you have one part doing two jobs, and that's why you get this weird good enough system. Okay. So that's sound. Um, I guess on that, imagine you're this hair cell up here responding to low frequency sound versus this hair cell down here responding to high frequency sound, right? Which one's going to break first? Exactly. By the age of 18, you've already lost like 5% of your high-end auditory processing. Because these little guys moving really fast, the more they move, the more likely they are to break off, don't get replaced, right? Over your lifetime, you lose your high-end, high-frequency hearing source. Okay? Yeah, that's enough. Let's talk about the other senses. Touch, we've kind of covered this. You have receptors in your skin. They communicate to the brain. Pretty simple. Pressure, temperature, excesses of pressure and temperature. The latter being nociception or pain. And then olfaction, maybe the oldest sense, the chemical sense. It's really simple. There's no stepping up or stepping down or mixing things or anything like that. And therefore, it's quite complicated. There's no simplification measure in here. Basically, you just have a receptor site in your nasal cavity for like any chemical that could be of importance to us as an organism. You know, tens of thousands of different kinds of receptor sites for different kinds of chemicals. And this is processed in the olfactory bulb. In other animals, this is the precursor to the frontal lobe. We sort of grew a frontal lobe out of the olfactory bulb and retained the olfactory bulb. This is right down next to the limbic system, next to memory and strong emotion. And so that could be why smell is so evocative. You smell grandma's cookies and get all misty-eyed and stuff, right? And then flavor or gustation. There's 6 basic flavors, and they're kind of encoded in different parts of the tongue, but different receptor sites respond to different classes of chemical. That gives you this stuff, right? We used to say it was 4. 15 years ago, there were 4 tastes, 4 flavors: sweet, sour, salty, bitter. All right. And then Japanese scientists kept telling us, no, you're missing one. You're missing the savory flavor. You're missing the flavor of raw chicken. We're going, hey, wait, who's tasting raw chickens? And we looked for it, and we kept doing the biochemistry and stuff, and dissecting tongues and whatever. We couldn't find it. Finally, a couple decades ago, I guess, we discovered the thing that the Japanese scientists were telling us about all along. And so we use their word, and their word is umami, right? And the way to remember this one is you go, ooh, mommy, that tastes like raw chicken. Okay? And then olio gusto, this is a new one even on me. This is the taste of fat. The satisfying taste of fat. Olio gusto. All right? Fat satisfaction, essentially. And that, yeah. Let's leave it there. That's going to do it for sensation. And we'll be back in a minute with a much more fun lecture on perception. Okay, bye.